Okay, so you're going to start the second talk, and Elena is going to tell us about directed spanners.
Okay, thanks. So yes, I'll be talking about directed spanners. This is based on recent joint work with my student Nitish Kumar, who's sitting right there, and he would be happy to talk to you about spanners afterwards. My former student Yang San Lin, and who's at Melbourne Business School now, and Ken Conrad from Purdue, who surprised me. He's also in the audience today. So directed spanners, this is a little bit of a different, well, I mean, it's the same kind of object. What we're looking here is at directed graphs, and we're looking at subgraphs such that the distances are preserved between pairs of vertices up to a stretch S. We can think of S as 2, 3 log n, a small number usually. And we want such subgraphs to have minimum size. So for instance, this is a graph that will show up a couple of times in the next few slides. It's essentially a complete graph with edges going from left to right. It's a dense graph. Every single pair of vertices is connected by an edge. What if we just wanted pairs of vertices to be connected by a distance 2 path? Could we get sparser things? And it turns out that if we look at the green subgraphs here, yes, it is sparser, and yes, every pair of vertices is connected by a path of length at most 2. Okay, so there are many, many variants. There are pairwise spanners where we don't need to connect all the pairs, but we just need to connect a set of pairs that is given to us in advance. There are spanners where the lengths are not just units, but general lengths. So we're given, so over there, S might not make sense as a stretch, and we're given the pairwise distances that we'd like to satisfy. So for each pair that we care about in D, we're given a distance DUV, and we'd like to output a sparse subgraph such that such distance constraints are satisfied. Okay. There are many other variants as well, and also, I guess, lots of applications and a couple of really good surveys that people can check if they're interested. I came to think about directed spanners in a very roundabout way. So first, we encountered these objects called transitive closure spanners. We define them this way because they are actually spanners on the transitive closure of a graph. So given a line, let's say a directed line, take the transitive closure. So whenever you have a path, now you can add an edge and take a spanner, a two spanner on this graph, for instance. There is also the kind of another view of spanners as you're given the graph and then you just want to add edges in order to shortcut the graph or the long paths, and so get a smaller diameter. Okay, so these were studied before. I mean, the transitive closure spanners are special cases of graphs that were studied before. They are also implicit in many works in circuit complexity, data structure, access control, and even monotonicity testing. And this is how I got into it. Surprisingly, I got to spanners from working on monotonicity testing. So this happened because, well, it's a paper from a long time ago, right? So 2008, at the time I was a PhD student. I was happily working on testing error-correcting code, so algebraic stuff, with Madhu at MIT. And then Sofia Raskolnikova visited Ronit, and Ronit introduced us. She told us about monotonicity testing on posets and general posets domains. And we started playing with posets and monotonicity testing, and somehow these two transitive spanner, two TC closure spanners kind of emerged as kind of like a general unifying framework for monotonicity on posets. So just very quickly, in case you're very curious, in monotonicity testing over, let's say, a line, we're essentially asking, we're given a function on the vertices, a real function, and we'd like to know whether it is monotone, right? So in this case, it really means that this array of numbers that we got is really sorted. Is it monotone or is it far from being monotone, which means you need to change it in a constant fraction of places in order to make it monotone. Okay, so maybe the first test you think about is, well, pick two vertices, random vertices, and check whether the labels are in order. Okay, so it turns out that the previous testers for monotonicity can be viewed as in the following way. So you put a two-transitive closure spanner on the line, and you uniformly pick pairs that form edges in this spanner. Okay, and it turns out that for the line, there is this very nice construction. It's a recursive construction. You take the middle vertex, connect everything on the left with the middle, connect the middle with everything on the right in the right direction, and recurse. This gives us an n log n size spanner. And it turns out that in general, you can get from a 2TC spanner a tester of query complexity, the number of edges in the spanner over epsilon n. So in particular, for the line, we get a log n query spanner, and then we asked the question, well, can you test other posets? And we show, for instance, that with log square many queries, you can test something like minor free graphs. Okay, so planar and more general graphs. Okay. Okay, so from here on, we also asked the question, what about algorithmic approaches? So how can we algorithmically come up with spanner on directed graphs? Actually, we initially thought about TC spanners on directed graphs, but it turned out that the initial approaches were giving us also spanners on the just directed graphs themselves. And that's pretty much what I'm going to talk about. I'm quickly going to switch into the more recent work, but before that, I should tell you what is known in terms of approximation ratios for directed spanners. So there is a lot known. Okay, let me start slowly. So for stretch 2, there is a tight log n bound. Okay, so what we saw for the line, it's just a tight bound. For stretch 3, there is initially there was an n to the 2/3. This is the sublinear thing here, the approximation ratio. It is hard within for larger stretches. It's hard to approximate within a factor of 2 to the log to the 1 minus epsilon. Our result was an n to the log to the 1 minus 1 over s approximation ratio, so just slightly sublinear. And it was the first sublinear algorithm ratio approximation for s larger than 3. But from then on, things got improved again and again. A breakthrough came through the work of Dinitz and Krautgemer, where they looked at more general things like arbitrary length edges, and the approximation ratio does not depend on S. And the best known so far are the bounds in this paper. where for s equals 3, it's an n to the 1/3, and for s equals 2, it's a square root of n approximation ratio. And there is also this pairwise variant where the bound is a little bit worse. So it's n to the 3/5 plus epsilon. And this is kind of the approximation ratio that we're going to compare our algorithms with. Okay, so the very high level approach is what you might imagine. So we're trying to solve some optimization problem. First thing you might think about is to try writing an LP for minimizing, computing a minimum size spanner. So what the variables would be, you have the x variables on the edges. So if you take an edge in the spanner, we'd like it to be 1, otherwise 0. And then we'd like to have a valid path between every pair, UV. So we have these path variables yp, and we sum over all possible valid paths. And we want to take 1, so the summation should be at least 1. And then if we took a path, then we should be taking the edge. And that's pretty much it. Okay, so we can write such an IP. We relax it to an LP, try to solve it, and round. One issue that comes up is, as you might imagine, there might be many paths between some pairs of vertices. And when that happens, the LP might give us a very small value solution, and then it's not clear how to round. So the idea that we had here, and we borrowed this from work in the undirected case for spanners, was to kind of break the approach into 2 cases. In one case, you have dense local graphs. So we're going to call the set of paths that are valid between U and V the local graph, right? And if the local graph is dense, we're going to do one thing. And if the local graph is sparse, we're going to do another thing. So if the local graph is dense, that means there are many paths that are good for us. If we sample, these paths are going to have many vertices. If we randomly sample, we're going to hit sample vertices, or we're going to hit vertices that sit on these paths. And then from there on, we're just going to try to connect them cheaply with the 2 vertices we're interested in. So we either do a BFS or some shortest paths, or later, yes. So the local graph is just the set of all valid. So for, let's say, a K-spanner is the set of all paths that are within a length K, that are within length K stretch. For TC spanner is it's the set of all paths of length at most K in the transitive closure. So it really depends on the problem. So this is a very good question. What is the local graph? What are the good paths for UV? So the vertices on the local graph are the vertices sitting on good paths. So yes, I'm looking for a path that is of length at most K times the length in the current graph. That's a good path. I'm taking all the vertices, putting them in the local graph. So it's not like, yeah, maybe you're thinking induced or
No, but when you say dense,
dense means that, yeah, there are many paths between U and V. So many paths would also mean many vertices. We're going to sample, we're going to hit a path with good probability. And from then on, we're going to do something simple like BFS or shortest path to U and V.
Density is just going to come down to number of vertices in this structure.
Yes, that's what it means.
Ultimately, you are just sampling.
That's exactly what it means, yes. Density is just many vertices here. So, yes, and in the remaining setting, when the local graph is sparse, then we're going to solve the LP and round in some problem-specific manner. Okay, so this picture will come up again and again because this is the very high-level approach for all the problems that we're looking at. It turns out that for each of the problems we're looking at, one has to redefine everything. What is the local graph? What is the LP? Maybe you want to look at another LP. How do you solve the LP? What else can you add? We're going to see junction trees instead of a BFS or shortest paths. So this framework is going to be repeated again and again, and maybe I'll even skip the slides where we're getting to other variants of spanners. So I'm going to talk about 3 papers. So these are all results for offline algorithms that we've seen so far. We have a result about online algorithms, and then 2 about even more general variants of spanners. Okay, so let's see what it means to solve this problem in the online setting. So in the online setting, the graph is given offline, okay? And then we're going to receive online the demand pairs and the distances between these demand pairs. So we want to satisfy this demand pair UV for distance DUV, okay? And the goal is to output a small size spanner H. Okay, so what does it mean online here? It means that that you solve something online. It means that if you picked an edge, you can't change your mind and drop it and pick something else later. So if you were greedy and picked an edge, you're stuck with it for the rest of the algorithm, even though it might be really bad for other paths, for other pairs. Okay, so in terms of results, okay, these are the results. We get an n to the 2/3 plus epsilon approximation, which can be compared to the n to the 3/5. This is for uniform lengths. And yeah, it is an open question whether one can tighten the gap. But we also get the k to the 1/2 plus epsilon approximation factor. So k is the number of pairs that appeared online so far. And more generally for arbitrary lengths, there is an n to the 4/5 approximation. And these results carry over to something called Steiner-Forest problems in the online version. So in this version, we just want to maintain that pairs are vertices that are connected remain connected in the subgraph. We don't care about distances. So I'm not going to say much about these. Okay, so how are we going to just at a very high level? The idea is the following. Previous frameworks can prove that this general LP plus sampling approach can give us an n over square root of opt approximation in the offline setting. And then they deal with the case when opt is small via kind of sophisticated techniques. And those techniques don't apply to our online, don't seem to be extendable to online. So the first observation we make is that opt is not that small, so it's at least square root of k, which leads us to the following observation. You can start adding shortest paths, essentially. As pairs appear, you don't really care about, you shouldn't worry that you might be adding too expensive things. The opt is large, so you can just simply start adding shortest, cheapest feasible path between the arriving pairs. So at some point, there is a threshold that we have to pick carefully, but at that time, we have to start writing the LP down and think about how to solve it online. Okay, so maybe now the first question, so why can we write it down? Because if we have the pair UV and the distance, we can look at the local graph and write down the constraints. And so solving the LP online essentially means that you want to update the variables in a non-decreasing manner. That's what it means. If you increased XE in one round, you cannot decrease it in the next one. It's at least that value in the next round. Okay, so it turns out that the seminal work of Bookbinder and Naor shows that if the LP looks nice in the sense that it's a covering LP, in the sense that all the constraints are covering constraints of that form, then there is a way to solve the LP online, and that gives us a log n competitive algorithm. And that kind of leads us to trying to solve the LP, to bring all our LPs for spanners into this covering LP framework. And that's not immediate, but with some work, one can convert the flow-based LPs of Dinitz and Krautgamer and Dinitz, Nazari, and Zhang into covering LPs, and then we do the usual thing: sample to solve thick pairs, or round to finish off solving the LP. Are there any questions? I don't think we do, but I don't know. Do you remember? Yeah, I don't think we do, but it's been. Okay, so do I have 5 minutes, or what do I? I'm not. Oh, okay. Wow, I was so slow then. Okay, so anyways, there are these nice tools called junction trees that essentially they are a union of in and out arborescences rooted at the same vertex. And the nice thing about them is that they approximate well spanners, and also they can be computed efficiently. Okay, there is the work of Chakuri, Ivan, Gupta, and Segev, where they show that junction trees with small density can be efficiently computed. And these are tools that we use again and again. The question will be, what exactly what is the definition of junction tree in our specific approaches? So just very quickly, what are the next two problems we look at? So I forget about online. Now I'm moving to generalization of spanners called directed weighted spanners. So in this version, the edges not only have lengths, but also arbitrary costs. So for the standard spanner question, the edges have cost 1. But you can imagine that you might need, you'd like other parameters to describe your problem. So in particular, you have costs on edges that are arbitrary, and the goal is to output a cheap graph H such that spanner constraints are satisfied. Anyways, this is a scary picture. I'm not going to go through it. One thing I should say is that our results for this more general version are very comparable to results in the unit cost setting. So n to the 4/5 plus epsilon. Also k to half plus epsilon, which also are the results that for the Steiner-Forest problem, which is what essentially this formulation generalizes. Okay. So here we unify spanners with standard spanners with Steiner-Forests. And as I just mentioned before, the high-level approach is the same. One is to redefine what the local graph is. So this time, its shortest path within some budget. And then one would need to rewrite the LP. It's a different LP. We need a new separation oracle. And we need to reprove the junction tree approximation results of Chekuri et al. For these new graphs. Okay, so now I'm moving to the last generalization of spanners. Okay, the third paper. These new spanners are called buy-at-bulk spanners, and they come up in questions about economies of scale. So buy-at-bulk means that if you buy an item in a bulk, on average, you'd pay less per item if you just bought it individually. So in the initial formulation, there is a subadditive function on edges, but one can simplify that formulation to networks where besides costs and lengths, you also have to pay per use every time you use an edge. Okay, so basically what we would like to output this time is a set of paths connecting demand pairs, such that we satisfy distance constraints, but also demands. And now now we would like to optimize the total cost, which takes into account the maintenance cost, which essentially says that every time you use an edge, you have to pay. So this delta, which is the pay-per-use cost, is appears proportionally in the number of times an edge is used. Okay, so when delta is 0, this is exactly the setup of weighted spanners. And when the DIs, there are no constraints on distances, DIs are infinity, this is exactly the buy-at-bulk network design question. So here again, our results essentially match the ones for both buy-at-bulk and pairwise and weighted spanners problems. And the new thing here is that we also can prove things for when negative edges are allowed. So negative cost edges or lengths could essentially mean gain in a network. So you don't always pay, you can also gain. And the whole framework that I mentioned a couple of times can be reworked with the new definitions, new costs, new demands to give us essentially similar results. So I'm pretty out of time. So in terms of open problems, tightening the approximation or the competitive ratios in some of the examples that we looked at is an open problem, or show separations. That's probably even harder. Even in the standard spanner problem, improving or understanding the hardness of the tight approximation factor of the spanner problems, it's an open question. And one can think of adding all sorts of further budgets, multiple budgets per edge, and generalizing this framework even further. Okay, I think I'm done. Thanks.
Questions for Elena? can you tell us the covering LP formulation? Is it a short formulation? Or I'm curious how you can write that fluently as well.
It's not a short, no, definitely not. So one can transform the previous flow-based formulations, but every time you're going for a covering constraint, you might end up adding exponentially. You might end up adding a lot of constraints. So one has to also tweak. So also tweak a little bit the bookbinder and our algorithm so that every time we so that the number of uses of the oracle is efficient. It's polynomial. But yeah, I don't have a picture of what the LP is.
It has exponential variables and exponentially many constraints.
I think constraints for variables for sure. Yeah, I mean, do you remember?
Any pair, isn't it between any pair? For the constraint, isn't it between any pair?
So there are multiple constraints between every pair. So every path has multiple constraints. So you could have exponentially many.
When you take the dual, you get exponentially many constraints for the dual. So you can solve that using a separation oracle afterwards.
Any other question?
No.
For the property testing motivation at the very beginning,
Uh-huh.
are there those like lower bounds or like how good is this Fader approach towards for
So at that time, I haven't followed up the literature, but at least for the minor free graphs, that was, I think, an improvement from square root of n to polylog. So it was pretty good. I don't know what the tight bounds are, but yeah, I'd be surprised if you can do it in constant.
like for the really general flow sets, for example?
So there are also there are some lower bounds, which we have in another paper, but I don't remember them. For like maybe low dimensional post set, I actually don't remember the bounds, but there are some lower bounds as well that say you cannot do better with this approach.
Sorry, my district question. So this online setting, is it? I mean, is this problem also studied for like related, let's say, leachability preserver and this one?
Right.
Like you know, the pairs are coming and you need to just maintain
The distances. So so the Steiner type. Yeah, I don't know. Do we have that? Let me see. I'm not remembering. Maybe not. I think we only have it for Steiner forests and standard spinors. I'm not sure. But I don't think so, though.
All right, let's thank Elena. I think we have a 15-minute discussion.